All right, so today we're going to talk about the chain rule. This is section 2.6 in your book. And one of the most important things for taking derivatives is to make sure that we take the derivative of everything. And so the rule we're going to follow for our derivatives, for all derivatives, is going to be the chain rule. So this isn't a new process. We're going to use the same rules: power rule, quotient rule, product rule, trig rules. The only difference is we're going to need to make sure that we do the derivative of everything, okay? So chain rule implies that there's a chain of things happening, and so for each of those things happening, we have to take the derivative. So here in your book, the derivatives of compositions. So it's just saying that if you have a function that is made up of other quote-unquote pieces, then we need to apply the chain rule. All of our functions are made up of pieces, and so whether it's written like this, or whether you have this, it doesn't matter. We're going to need to take the chain rule and apply that. Simply means take the derivative of every piece, but in doing that, you need to take them in the appropriate order. Okay, so let's go ahead and do an example. Okay, find dy dx if y is equal to the cosine of x cubed. Okay, so rather than do this the long way, I'm going to go ahead and jump right into the chain rule. Dy dx means take the derivative of y with respect to x. So x is our variable. So we're going to start by writing the original function. And so for the inside, we're going to start on the inside. We always start inside out. We need to take the derivative of the inside. Okay? So what's the derivative of the inside? The derivative of the inside is going to be 3x squared. Okay, the derivative of the inside is 3x squared. Now, remember with trig, whatever's in here, we're not going to change. So now what I need to do is take the derivative of the cosine component. And so going back to section 2.5, the derivative of cosine is negative sine, and the quantity stays the same. So in here, just to review, we have two pieces. We have an x cubed piece, and we have a cosine piece. So when I'm done, I should have two derivatives. I should have a derivative of the x piece, and I should have a derivative of the cosine piece. So what we're really doing is we're breaking down the function into its pieces and then taking the derivative of each piece individually. Okay? Find dw dt if w is equal to the tangent of x and x is equal to 4t cubed plus t. So what we're going to do here is we're going to write the original functions, but we're actually going to look at what this is asking us. This piece is asking us for the derivative of w with respect to t. So the derivative of w with respect to t. When we go look at the original equation, we can see that w is in terms of x. So that's a problem because this is not going to get us to here. So what we want to do is say, okay, oh look, they gave us this, so we need to plug that in here. So we're going to do a direct substitution piece first. So we want to go ahead and plug that in. The tangent of 4t cubed plus t. Okay, so the first thing we want to do is say, okay, we have two pieces. We have the tangent component, and we have the inside. All right, so here's what we're going to do. We're going to take the derivative of the tangent piece and then just leave it alone. So what's the derivative of the tangent? Go back to section 2.5. The derivative of tangent is, sorry, technical difficulties. Okay, where was I? Okay, so we made the substitution of x, excuse me, for tangent into the tangent equation. So here's our actual equation. So now what we want to do is we want to take the derivative of just the blue piece, just the tangent. So the derivative of tangent is secant squared of whatever was in parentheses. Okay, that's the blue derivative. So we're going to leave this. Now we have the black piece. the inside. So take the derivative of the inside. So the derivative of the inside is going to be (12t² + 1). And then we're done. Okay, so we had two pieces. We had the black piece here, we had the black piece, and there's its derivative. And then we had the blue piece, the big tangent, and then that's the derivative of that piece. Notice, this is very important. Inside did not change. Okay, the inside did not change. So I took the derivative of the tangent piece, but this does not change. Okay, that is very, very important. Please do not take two derivatives at once. Take derivative of each piece independently. Okay, so your book uses some different notation, and it simply says if I have a composite function, okay, you take the derivative of the outside, leave the inside remain unchanged, and then you take the derivative of the inside. So each time you have an outside and an inside quote-unquote piece, you have to take a derivative. Only changing one item at a time. Notice when I take the derivative of f, I leave the g piece alone. Okay? So this is just another version for notation of how the chain rule can be written. Okay? The application and the process is exactly the same. Okay, so find h prime, h of x is equal to cosine of x cubed. Now, you have multiple ways to do it. I'm not going to revisit it. I only do it one way. Option 2 is to take the inside and make it be u. So I'm going to do it the same exact way. And so what I'm looking at now is the outside. And the outside piece is cosine. So the derivative of cosine is negative sine. Notice I'm going to leave my parentheses here the same. That is going to remain unchanged. But now, whatever was in those parentheses needs a derivative. Okay, so now if I come back up to the original problem, what was in the parentheses is x cubed, and that's x cubed. So now I'm going to take the chain rule and apply it here. So we have this. And now the derivative of x cubed, which you know from section 2.2 power rule. Oh, 2.3, I guess it is. And I'm just going to write it the same way I wrote it on the first slide. Keeping in mind, I'm going to put the parentheses so that we don't get confused there. And this is just notation. Prefer to write the constants and the whole exponents in front. Okay, same thing. Same exact thing here. This is just an example written out in the book, keeping in mind that this is tangent squared. Tangent squared. So when we take the derivative of the big component, it would be something squared. So that becomes two of those somethings. In this case, the something is tangent. Now I take the derivative of tangent x, which is here. So you might write this as something squared, which it's 2 times the something times the prime of the something. Okay? That's all we're doing here. Same thing is true here. Same thing is true here. You had something to the 1/2. That becomes 1/2 of the something to the negative 1/2. But now, up to this point, your derivative inside has been 1, so we've neglected to tell you that you had to do that. Okay? You've been doing it all along, but we've been selective in the problems that we've given you. Okay, so example 5. So find the derivative of the following. So let's go ahead and take a look at A. That should be an A, not a D looking thing. I'll say A. And the derivative of sine of 2x. Okay, so first things first, we're going to take the derivative of sine. The derivative of sine is cosine. That remains unchanged. But now I need to take the derivative of the inside, which is 2x. Well, the derivative of 2x is simple. It's 2, now cosine of 2x. Okay, the important piece here, again, I am stressing this because it is very important. This is still here in parentheses. If you look at your final answer and whatever was in here is no longer in here, you've done something wrong, okay? Experience says that students make that little mistake. All right, so now we're going to take the tangent of x² + 1, and we're going to prime that, Okay, notice I'm using slightly different notation just so you can get in the habit of exchanging notation to whatever you're comfortable with. This d dx is the same thing as saying prime it, derivatize it. So the first thing I want to do is take the derivative of tangent. The derivative of tangent is secant squared of whatever was in there. Then I'm going to take the derivative of whatever was in there. So when I look here, I'm going to put that here. And now my final answer, I'm going to take the derivative of this piece, which is going to give me 2x, and then this all just comes down. Secant squared of x squared plus 1. Done. Okay, notice I'm only changing one thing per line. All right, let's take a look at C. C is written as the cube root of x cubed plus cosecant x. Okay, x cubed plus cosecant x. So now what I want to do is prime that. But I like writing it with the exponents because then I can remember the power rule. And this is all to the 1/2 power. So I'm going to prime that. So what I end up with, something to the 1/2 power is then that thing to the negative 1/2 power, but then I want to prime that thing. Okay, so that thing, so I've done the outside first, now I need to do the inside. So now I want to take the derivative of the inside. So the derivative of the inside, this piece right here, is going to give me 3x squared minus cosecant x cotangent x. And that's a negative. So the derivative of cosecant x is negative cosecant x cotan x. And now I want to write my final answer in appropriate terms. So I'm going to go ahead and write it as 3x squared minus cosecant x cotan x all over 2 square root of x cubed plus cosecant x. And I'm going to go ahead and stop because that is done. Okay, that is done. All right, scrolling back up just so I can see the D and E. And of course, I'm probably going to screw this up. So I'm going to write it on the board next to me for a second. And then 1 plus x to the 5th cotan x to the negative 8th. Okay. So let's go ahead and tackle D. And D says I want to take the derivative of that. Derivatize. So when I derivatize this, I want to say, okay, that's something to the 3/4. So that's going to be 3/4 times the something to the negative 1/4. And then I'm going to multiply that by the derivative of what was in the parentheses. So inside my parentheses, I had the x squared minus x plus 2. And now I want to take the derivative of this piece. So the top part's going to come down. It's going to be 3/4 x squared minus x plus 2 to the negative 1/4. But now I'm going to multiply that by 2x minus 1. And so I'm going to record my final answer as 3 times 2x minus 1 over 4/4 root of x squared minus x plus 1. Oh, my bad, plus 2. Plus 2. Okay. So there's your final answer. Again, baby steps, right? So we pulled the exponent down here, subtract 1 from it. 3/4 minus 4/4 is negative 1/4. The inside remains unchanged. The inside remained unchanged. Now I take the derivative of the inside. Okay, now take the derivative of the inside. And the last example is E. And E says 1 plus x to the 5th cotangent x to the negative 8th power. And just because this one is long and ugly, I'm going to go ahead and move it down here. Okay, so we have a couple of issues here. And so we're going to do the first one first. What I'm really going to do is prime that, take the derivative of. d dx of this function. So anything to a power, so negative 8 becomes the power. That thing is now going to be to the minus 1 from that. So negative 9th power. Then I need to take the derivative of the inside. Well, the derivative of the inside, because of that x to the 5th times cotan x, I'm going to have to use the product property on that. I have to use the product property. So I need to take the derivative of this, but in order to do that, I have to use the product property. So as a little aside, I'm just going to come over here, and I'm going to call this one f and this one g. And so f prime is going to be x to the 4th, and g prime is going to be negative no space. Let me get more space. G prime is going to be equal to negative cosecant squared of x. So now the first piece stays. So negative 8 times 1 plus x to the 5th cotan x to the negative 9th times. Now the derivative here, the derivative of this is just 0, so we don't even need to worry about it. So now we have the derivative of x to the 5th, this piece, x to the 5th cotan x. So the derivative of that is f prime times g plus g prime times f. And so that looks a little ugly, but remember, I don't have the 0 plus here because that doesn't need to be written. So now I'm going to try to write this in terms of proper format. So I'm going to have negative 8 on top times, this is going to read x to the 4th cotan x minus x to the 5th cosecant squared x all over 1 plus x to the 5th cotan x to the 9th. Okay, so again, we actually had to use chain rule here. We used chain rule here because I took the derivative of cotan x, which is negative cosecant squared x. And what's the derivative of x? The derivative of x is just 1. So you're using the chain rule even with something as simple as this or this. You just aren't used to seeing it. So, for example, x to the 5th is actually, hello, Miss Collins, check your work. That's a 5x to the 4th. 5x to the 4th. And then the derivative of x is just 1. So this is 5x to the 4th times a 1, but we don't write the times 1, okay? So 5x to the 4th, cotan x, derivative of f, the derivative of g is here, and so we use the product property to get that. Okay, so let me just write that here so you remember. So we're using product property, power rule, trig identities. We're using all of those ideas and still completing our derivatives, but now the chain rule requires that we apply them all at once. All right, example 6. So this one, we're just going to show you a couple of different problems now. This is just funky, ugly mu and omega little signs that we use, Greek symbols. It's the same exact thing. You can change that to a y if you want. It doesn't matter. So let's do part A first. It says take the derivative of this with respect to x. So x is the variable. So the first thing we're going to do is take the derivative of sine. What's the derivative of sine? It's cosine of that junk. And then we need to take the derivative of that junk. So the junk is 1 plus cosine x. Now we need the derivative of 1 plus cosine x to the 1/2. Okay, so I'm going to bring this down because this doesn't change anymore. And now I need the derivative of this, which is going to be 1/2 this junk to the negative 1/2 times the derivative of this junk. So there were 3 pieces now, and I should have 3 pieces when I'm done. So I'm going to bring this down because it doesn't change. Notice my parentheses. This piece is going to become and now the derivative of this last piece, the derivative of this, is going to simply be derivative of 1 is 0. The derivative of cosine is negative sine x. And what's the derivative of x? The derivative of x is just 1. So I really don't need to write it, but I'm writing it just to show you we have always applied the chain rule. And my final answer is going to be negative sine of x times the cosine of the square root of 1 plus cosine x all over 2 times the square root of 1 plus cosine x. That, my childrens, is my final answer. Okay, so every time I have a piece, I have a derivative. So let's look up here for a second, and I'm just going to show you. I had an inside piece. I had a square root piece, and I had a sine piece. Okay, so there's 3 circles there. There's a black, a red, and a green. Notice, I should have 3 lines of derivatives. So I have the first line. I have the second line. And I have my third line. I took 3 derivatives. Each time I took a derivative, only one thing on my line changed. So this is my first change right here. Here's my first change from sine to cosine. My second change is right here from the square root to its derivative. And then on the third line, I went from the 1 plus cosine to the negative sine x. Okay, so every time I take a derivative, I'm only changing one piece. Okay. Let me close these parentheses. There we go. Okay. So now the mu is the secant of omega t. Well, this is a constant. So you can look at that as like, I don't know, look at that as like a 2, a 5, a 7. Not a negative, preferably. But okay. So what we want to do first is we want to take the derivative of the secant. What's the derivative of secant? It is secant of that junk times the tangent of that junk. Well, that junk is this. And then we need to take the derivative, write it correctly. We need to take the derivative of the junk. All right. Well, secant of the square root of omega t times the tangent of the square root of omega t stays the same. Now the derivative of omega t is going to be 1/2 that stuff to the negative 1/2. Now times the derivative of that stuff. Okay? So final line is going to be secant of the square root of omega t times tan of omega t times 1/2 times the square root of omega t. The derivative of, remember, this is just a constant, like 2x, 4x, 8x. The derivative of this is just going to be omega. And that is my final answer. I'll take final answer for 1,000, Alex. Done. Okay? All right, you are now going to do the quick check exercises on page 178. Notice the answers are on page 181. For my students coming in, please, please, please show me your steps. And when you have to use the product or the quotient rule, please note that information on the side. Okay? If you have any questions, please go back, make those notes in your notes. Where you had questions, what you didn't understand, what was confusing to you. Please mark that in your notes and then bring those questions to class tomorrow. All right, good luck.